In this video, we will learn how to write our first MS-DOS program in assembly language. Now, before we get started, it's important to understand what assembly is. It's not one language that covers many CPUs with a consistent syntax. In fact, every assembler syntax is going to be different for each CPU you use, even if they do share similar instruction names. So, assembly for Z80, Alpha, MIPS, PowerPC, and whatnot could be seen as different languages in their own right. In this tutorial series, I'll focus on 8086 assembly with MS-DOS, as that's a pretty sensible starting point, and it will cover a very wide range of computers. Now, if you're just getting started with programming, assembly might not be a good starting point, especially in the modern age where compilers such as GCC have become very efficient at code generation. In the majority of cases, you shouldn't need to write assembly code of any kind, really, but if you plan to write programs for older hardware where CPU cycles are not entirely abundant, assembly programming can be useful. If you are an absolute novice and just want to get your hands dirty with basic programming concepts, I recommend starting with QBasic for MS-DOS. While QBasic is much slower, it is a lot simpler to work with and provides on-screen help for any function when you press the F1 key. So, for instance, let's type the following command here, and we'll say print the result of 5 multiplied by 30 is a 5 times 30, and we'll go ahead and run it. We can press Shift F5. And as you can see, it says the result of 5 multiplied by 30 is 150. And press any key to continue. So, that's a pretty good way to get started programming. It'll offer you a ton of functions that you can use. It makes certain things in MS-DOS easier to perform, like, say, drawing graphics on the screen or making the PC speaker beep, those sorts of things. But assembly is our point of focus here, so we'll get out of here and we'll open up a plain text editor. You can use Notepad, Vim, or anything like that. And of course, before you do so, though, you should remember to install an assembler of some kind. I prefer to use Flat Assembler because it has a very straightforward syntax, and it's a multi-pass assembler, so you don't have to worry about, like, defining how short or far your calls are. Of course, Microsoft Assembler, Turbo Assembler, and NetWide Assembler are good options too. So once you got that installed and you've loaded it into your path environment variable, you'll want to load up a plain text editor. In this case, I'll just use the MS-DOS editor. I was going to say new prog.asm. ASM is going to be the file extension you'll use for assembly source code files. So now let's write our first program. Starting with the first line, we're going to type org 100h. The first line with the org directive sets the origin of the program. All MS-DOS COM programs originate at a memory location of 100h, so that line is needed to create such a program. Note the trailing h here. This indicates that this is a hexadecimal or base 16 value and really means 256 in base 10 or decimal. You can write it differently, like for example you can type in 0x100 here, or you could just write 256 to represent a decimal value, but we'll type in 100h here. Just be mindful of the differences of hexadecimal and decimal numbers. I urge you to familiarize yourself with hexadecimal and binary enumeration, as it'll really come in handy as you develop your programming skills. Now, the next line will contain a move instruction. Move basically copies a source value to a certain destination. The source and destination values could be an immediate value like 9, or a certain buffer in memory, or it could be a CPU register like AH or AL. But in this case we're going to do 9. Now I should explain what CPU registers are in this diagram. Now, the Intel 8086 CPU contains several registers, 4 which are designated as general purpose, as seen here. They are AX, BX, CX, and DX. Even though these registers are general purpose, each one of them also contains its own specialized functions, so you should be conscious of what data is being allocated to which registers. Like, for instance, this count register CX is often used in 8086 assembly to keep track of the count of certain things, particularly for iterating repetitions. 8086 registers are 16 bits wide, so they can store numeric values from 0 to 65,535, and these registers can be addressed in their entirety with the trailing X, or you can address the higher or lower half of a register by replacing the X with an H or an L, respectively. One half of a register can only contain values from 0 to 255, as would be cutting it down to 8 bits or 1 byte. For example, AH is being assigned the immediate value 9. And of course this has no trailing H or a preceding 0x, indicating it is a decimal value, although technically, because it is under 10, it will basically just mean the same thing. AH can later be recalled somewhere else in the program and would be represented as such, but do be mindful that if you try to work with the entire AX register after assigning a value to the upper half, you'd be dealing with a value like 0900H, which is a lot higher than just 9. So if you wanted to address the lower half, the value of AH would be excluded, and so AL would not contain the value 9 unless it did already. Keep this in mind when you're working with registers. So now we'll write another move instruction on a new line. In this case, we'll fill the entirety of DX with a pointer called string. Perhaps I should go ahead and define this pointer right now at the bottom of the program. Down here, this is basically some raw data to be used in the program. We've given it the label string, and we've used dB to indicate we're defining a byte or a string of bytes. This could be a single numeric value like 43. It just so happens to be a string of multiple bytes enclosed in single quote marks. The single quote marks here tell this string that these characters are to be read literally. If they were not, then if they were not enclosed, then the assembler would either throw an error or would try to treat a number as if it was an actual value to be processed. A numeric value. Now, when this program is assembled, the assembler will automatically replace the name string with the exact number that needs to be loaded into DX to represent the memory offset where the string starts, because technically you cannot load a string into a CPU register, but you can load the offset of a string into it, and that string can then be used by a certain function. And this is one of the key conveniences of assembly programming, as it will perform some of the heavy lifting of writing machine code for you, so you don't have to go back and update so many offset values when you add more code to your program. And so no matter whether the offset is 39, 40, 41, or 42, all you have to do is type string, and the assembler will automatically keep track of where the offset is and what value needs to be put in place depending on where the string is located in the program, and that offset 41 will go into DX like so. And of course you can also replace the name string with just about any, almost any name you want. Some names are reserved, but you could type in something like bottle, but we'll just type string for small contextual purposes, as this is a very, very small program. Now let's create another line which will introduce another instruction, int, not to be confused with an integer in the world of C programming. Int means call an interrupt. A program can manually trigger an interrupt like 21H, which is where the MS-DOS API resides, or an interrupt can be triggered by a hardware device like the keyboard. So say every time you press a key, the CPU is interrupted so it can process the key and place it on the screen. In the case of interrupt 21H in MS-DOS, the values of AH and DX would tell the computer to display a string of text at the given offset, as described in this page. Say DX is a $ terminated string, and AH would be equal to 9, and that would point to the write string to standard output function. Now, of course, that's something you may have noticed earlier, that I put a $ after the hello world message, and that's because the function expects the string to be terminated with $, so that it doesn't go on and on and on and potentially print out so much more garbage. Now, a more sane program would use a 0 or a null byte terminator, but for whatever reason, as DOS was being developed, they decided to go with a $, as the string terminator. And so there are much better ways to print a string in your assembly DOS program. This is just the simplest one. And of course, there's a lot more to interrupts in assembly. As I mentioned, keystrokes, that requires interrupting the CPU to process keystrokes. We'll talk more about those later. For now, you just may wish to refer to this web page to review more of the functions of the MS-DOS API and perhaps experiment with them. Just be careful that you don't mess up anything or perhaps destroy important files, because some of these functions can be destructive. So I would recommend that you experiment with programming on a separate machine, or perhaps a virtual machine, or you could also use DOSBox. So whenever you want your program to finish its execution, it's very important that you tell it to exit, otherwise it's going to coast along aimlessly, potentially treating garbage data as instructions, which could cause your program to crash or even destroy data. So we'll tell the program to exit the DOS by loading AX with 4C00H. and of course that just means AH is going to be equal to 4CH, and AL is going to be our return code, and we can define both of these halves of the register at once by typing move AX 4C00H. The return code could be something like 53 if you wanted to indicate that there is an error in the execution of the program, perhaps by the user or something else. But 00 is generally the accepted exit code for when a program is to terminate normally. And this is another MS-DOS API function, so in order to execute this like so, we've got to type int 21h and with that we have a complete program written entirely in x86 assembly. So let's go ahead and make sure you save this and exit. And now we can run the flat assembler, which is FASM, followed by the name of our program source file, newprog.asm. Now, one thing to note with this particular assembler, it needs to be run in protected mode and does not come with its own protected mode interface. What this means is that whenever you try to run flat assembler in a real mode MS-DOS prompt or MS-DOS mode after exiting Windows 95, this program will not work without an external DPMI interface. But NTVDM and DOSBox come with their own DPMI, as does Windows 95 when operating an MS-DOS prompt within the graphical environment. But in a real mode DOS prompt, you have to supply one yourself. Of course, flat assembler builds also exist for native Win32 and Linux environments, so you're most likely better off using those. They are just as capable of creating MS-DOS programs. I just wanted to clarify how flat assembler is run in MS-DOS. So anyway, let's go ahead and assemble the program. You should see some output like this. It'll say 2 passes, 24 bytes. And this would indicate that the assembly was successful. And so if you see any errors, you should go back and make sure that you type the syntax correctly. Now, if we do a directory listing, we'll see that our COM program has been generated. Of course, I already had a .exe program here, but I just deleted that, so I will show you how to create an exe program after we go ahead and run this. And we see we have our string printed, hello world. So there you have your first MS-DOS program. You can run it on practically any x86 based PC hardware you want, including the very first IBM PC, after booting MS-DOS from a floppy or hard disk. Before we go though, let's go ahead and turn this into an exe program, because while the COM format is certainly fine for very tiny programs that have very specialized purposes, it's not exactly the most ideal for, say, larger programs as COM programs only ever take up an entire 64 kilobyte memory segment, and for that reason too, exe programs could be more efficient on memory. So let's make a few changes to this program. We're going to get rid of the org 100H line, and we're going to type in format MZ. This will tell Flat Assembler that a MS-DOS exe program is to be generated. With an exe program, you also get the benefit of being able to use a stack with your program. And we can define a size for the stack right here, which would be 100H. And this would indicate that this would be the size of 256 words. A word is 2 bytes, so that's technically 512 bytes. We'll talk more about this stack later. For now, we just want to get our program turned into an exe version. And for good measure, we'll add another directive, U16, which should enforce the use of 16-bit code if you really want to make sure you can run your program on a IBM XT or AT compatible machine, as some programs are designed to be 32-bit, which means they would only be able to run on a 386 or later. Now, after defining these directives at the top of the code, we'll need to write 2 additional instructions for the CPU to execute: push CS and pop DS. Push and pop are instructions related to managing the stack, but all you need to know now is that these instructions will align the data segment with the code segment. Of course, you probably don't know what either of those are. It's a memory segmentation related thing. But either way, this for right now is quite appropriate for a tiny program like this. While I'm at it, I should also add a line feed to my string, a line break. And to do that, I'll get rid of this $sign, and then I will append the string. After the single quote mark, I'll add a comma and add a numeric value of 13, which means carriage return in the ASCII table, followed by 10, which means line feed. And these 2 characters represent a line break in MS-DOS and Windows. If you're programming for some Linux or Unix flavor, all you'd really need is just the 10, but for DOS programming, the carriage return 13 is necessary. And then, of course, the string must also be terminated with a $sign again. So, let's save the program. And we'll go ahead and assemble it again. And you see our program is slightly larger. It's not so much so, it's only like maybe around 40 bytes larger because of the way an exe program is formatted. It's not a huge deal. Our program should still take up less memory than a COM program given how small it is. So Now if we run another directory listing, we'll see our program, our exe program exists now, and we'll go ahead and make sure we specifically run the exe program. And we'll see we have hello world and the extra line break here. Compare that to our com program, it doesn't have that line break in there. So that's about it for you have just written your first MS-DOS exe program. So as we progress further, we'll learn how to perform arithmetic operations and display those on the screen and get user input and even do some cool things like displaying graphics. So take care. I'll see you in the next one.